Okay, hello everyone. My name is Vicic. I'm a postdoc researcher here at ICTP, and I work with micro earthquakes and observational seismology in general. So in the next few days, I will show you a few examples, how to work with the data, where to get the data that you would maybe be interested in. And we will try to use some computational methods to detect earthquakes, to pick phases of the earthquakes, and calculate the magnitude of some small earthquakes, and so on. You will see. So first, the first question I have for you is, so last 2 years, students followed a course on Python, but I do not know if this is the case this year. So did you follow the course or not? Oh, no, yes. I cannot hear anyone, so you have to unmute if anyone wants to say something. Because today, I mean, today most of seismological work is done with different open source codes, which are more or less written in Python or some other language. But just a second. Sorry. So yes, more or less all the codes are written in Python, and data processing, first steps of data processing.
Yeah, hello.
Huh?
I don't know if it's only me. Like it's like I cannot hear you well.
Anyone else has problems? I mean, do you hear me?
Yes, we cannot hear you very well.
Oh, well, just a second. Just a second. Let me try something else. Try to use different set of microphone. So can you hear me now?
Yes.
Yes,
okay.
yes.
Okay, so perfect. let me start again. So my name is Blaž Vicic, and I'm a postdoc researcher at ICTP, working with observational seismology and micro earthquakes. And in the next few days, I will show you how to work with seismic data. So we will learn where to get the data, how to download it, how to do basic pre-processing on the data, and how to detect earthquakes, how to locate them, and how to, let's say, calculate the magnitude of the small earthquakes. So first question I had for you was...
Now we can hear you very well.
Okay.
Thank you.
No problem. First question that I had for you was if you followed the Python course this year, because in previous years there was a Python course organized, but this year everything is a bit different. So
we had just introduction on Python. It was not very.
Okay, I think this for what I will show you, this should be okay, because we will not go, you know, very detailed in writing our own codes. We will use pre-existing codes, but if you have some introduction to Python, so if you know the logics, you know how to loop through the data, then this should not be any problem. But anytime you have any questions, please stop me and ask. I will try to answer everything that is, you know, that's possible.
Okay.
Thank you.
Okay, so you see my screen, right?
Yes.
So today, on the first day, we will go through. Let me start somewhere else. So to work on with the data, to do the basic pre-processing that everyone has to do, we will use the open source package. It's called OpSpy, and I sent you the in the README file. I asked you to install this on your computers so you can try to run this also on your own. So this is a package used for seismology. It's written in Python, and somehow it came. It came out a few years ago, and it's now very much used in seismology. A few years ago, this was SAC, if maybe you know it. Today, people mostly use this because it's up to date, and many more people use it. And if you know Python and some basic programming stuff, this is very simple to use, and you can write your own codes to do a big projects if you want. So in general, what I thought, because it's a bit more complex this year than previous years, maybe the best thing is that we go through the code that I have and I show you how it works. And then let's say by the mid of this week, I will send you these Jupyter notebooks, so you can try to run this on your computer. What all the things that are here in the Jupyter notebooks are very simple, so you don't have to have a big computer to run it. And then you play with it, you try to do something else, something more, and then for the exam, I thought to maybe give you some very, very simple exercises to run and few questions, and that's it. Then the other will take the course. So next week you have, I don't know who exactly. So each of us will give you some questions that you need to answer. And so let's say if I send you the final assignments and questions by the end of the week, then maybe if you answer them by mid-April and send the answers back to me, this would be okay. I will write to you an email exactly how this will go, but more or less this is something like this. It will not be very, hard, because the main thing here is that you familiarize yourself with these softwares and codes that you can use, because it will be very useful for you. Okay, so first today I will.
I have a question. I tried to install the Jupyter, like the Anaconda, on my desktop. The desktop but when I tried it, they asked me for a password. I used to enter my password, but
so you wanted to do this on the ICTP computer?
Yes.
I mean on the computer desktop. In the office, desktop.
Yeah, in my room, like we have a desktop in our rooms. So when I enter my password, it doesn't work. They used to tell me, sorry, your user is not allowed to.
Okay. But do you maybe have a laptop where you could do this?
Okay, I have a laptop, but that one, I have a Anaconda spider on it.
Yeah, but I mean, this is, yeah, okay. But with Spider, I don't know if you can use this Jupyter notebooks. So you should also install the Jupyter notebook on it.
Okay.
Yeah. Okay. I mean, try, but if you have any problems, please send me an email and we can chat and solve it. But with the computers of the ICTP, yes, this could be a bit complicated. I don't know exactly, because last 2 times I had this course, everyone used their laptops because we were in class. So okay.
Thank you very much.
Okay, no problem. Okay, so today what we will look at is
We will look at these main parts of OpSpy, so how to get the data, how to download waveforms, so the seismic data recordings, how to get information on the stations that we can use, and how to get earthquake catalog of some specific area that we are interested. So first, in Jupyter notebooks, I hope that you went through the tutorial, the YouTube tutorial that I sent to you. So I don't want to lose too much time, but basically here, these first windows are just meant to import Python codes that we will use for our course. So let's say here in this second window, we import in the first line so-called client. This is a small package for OpSpy that is used to download the waveform data, and so we don't have to invent, hot water. We already have this inside of Python OpSpy. Then we will use the Matplotlib, which is a library used for plotting to make graphs. We will use NumPy. NumPy is a library for computational stuff, and this OS is a library which gives us availability to interact with the operating system in our code. So the main difference between these Jupyter notebooks and the code that we write in a script is that within this Jupyter notebook, we can, write a code, run a part of the code, and change something and run it again. We don't have to run the whole code. If the code would run for 5 minutes and we only need to change a small part, this is much better. It's much faster. But as soon as you want to, you use these Jupyter notebooks for developing of the code. When you have your code ready, you put it in a nice script, you put it on the, I don't know, HPC and run it on multiple cores at the time, and that's it. Okay, so then Python has these functions that we write with def. If we start to write it like this, then we make our own function that we can call multiple times later, so we don't have to copy and paste the code all around. And here is a simple function that I wrote that we will use for plotting of the waveforms, because the plot argument that you can call with the OpSpy, it's not so nice. And if you have a lot of data inside, the picture becomes a bit messy. So I redid this with this command. Okay, so when we work with earthquakes, normally the first thing we are interested in is earthquake catalog. So let's say I want to work with earthquakes that happened in, I don't know, in East African Rift. I go to some website, maybe there is some institute that has this data, or maybe I go to IRIS. I will show you this later. And I download the earthquake catalog from there. These earthquake catalogs are, depends from where we get them. Some are very good. They have a lot of small earthquakes inside. They have information on the errors, horizontal, vertical errors, and so on. Some earthquake catalogs are not so good, only consist of big earthquakes, let's say magnitude 4 and above. So this is always, different things we can check, but I will show you there are some places where you can get quite good catalogs, but this of course depends on the seismic network that is available in that region. So, okay, first let me, I need to start running this code, otherwise it will not work. So, okay, in OpSpy, when we download a catalog, the catalog is basically, so let's say this red square here, this is a catalog. And a catalog is actually just a list of small events. And events are, one earthquake is one event. So if we have a catalog with 10 events, we will have a catalog of 10 earthquakes inside. And each of these events is just, you know, a group that holds inside many more information. So let's say we check the first event in the catalog, and this event will have information on origins. So this is latitude of the earthquake, longitude, the depth, origin time, so when the earthquake happened. Then we have information on magnitudes, because let's say each earthquake can have different magnitudes assigned to it, a local magnitude, a moment magnitude, I don't know, a coda magnitude, let's say. These are some magnitudes that were used in old times. So we have this list of different magnitudes that we can access to. And then good catalogs also have information on peaks. So when the earthquake is detected on a seismic station, we can pick the phases of the earthquake, P and S phase, or some other phases. And we will have information on these peaks within our catalog. For larger earthquake, depends again where you get the catalog from. We can also have information on the focal mechanisms of this earthquake. But as you will see, if you will use this data, many times when we download the catalog from some specific place, the information on peaks and focal mechanisms and other things will not be provided. I know that for some earthquakes, USGS does provide peaks, but I don't know how exactly they produce this. I mean, is this just automatic detections, or these are checked and verified peaks? And then we have another event and so on. So what we will do now, I will show you how we can download a catalog of earthquakes. In our example, we will use data from the International Seismological Center, ISC. So if we go to this website, this is their website, and they hold earthquakes from 1964 up to present. So you can get all these earthquakes from all around the world from them. But those up to 2018 are reviewed, so their location is much better than some automatic location. But after 2018, they are not reviewed, so you need to take care with them if you look at, let's say, phases and location. So yes, this is the one of the providers. Then you have, let's say, USGS. This is the American survey. They also provide event databases. Then you have, let's say, it's hard to do this here. So you have USGS, you have INGV, you have ISC, and so on. And if you want to use OpSpy with these providers, if you go to the manual of OpSpy, you can see which are supported already by OpSpy and which are not. So if you want to work with USGS or INGV, it's available. But if you want to work with some, you know, very small local provider, you will not be able to download the data from there. Okay, so we will use this ISC. And what we will do now, we will define the time of earthquakes we are interested in. So I want a catalog between 2018 and 2020. So basically 2 years of the data. And I can define latitude and longitude of the area I'm interested in. So I will define minimum latitude and maximum latitude, and minimum longitude and maximum longitude. So here, this is defined.
Yeah, please, I have a question. In where we are defining the date, date you inputted 2018 and one.
Ah, yes, sorry. Okay, so the first number is year. This is the second one is month, day, hour, minute, second. So because I just want from 1st of January, I can easily delete this. So I don't need information on hour, minute, and second. But as you can see here, I use this UTC date time. And this is, again, this is a function that comes from OpSpy. And if you go to the manual of OpSpy and you search for UTC date time, you will get all the information that you want to have about this UTC date time. Also, I think, let me try to okay. You see, in Jupyter Notebook, you can write also the name of the function, press tab, and search what things can be done with such objects like UTC date time. Okay, so and here I set latitude and longitude, the minimum and maximum, and the same for the longitudes. Okay, so I can start this, and here with this command, so I take the client, which I defined here, and I call the get events function on it, as I said before. So I can write here client dot and press tab. You see these blue things are stuff that is available for the client. So get events, get stations, get stations bulk, get waveforms, or you can write help and see what happens. You can write .help on a function. It gives you all the information that maybe you are interested in, what goes in this client. Okay, so now, as you see, I defined start time, end time, minimum longitude, maximum longitude, and so on, and I can start to download this catalog. It takes some time because my internet at home is very slow. And okay, you see, I was able to retrieve almost 600 earthquakes in this specific area in a span of 2 years. So now what other things that I can do with this catalog object is, let's say I can make a plot. So in this way, I can make a plot of my catalog, so you will see where these earthquakes are located. These are very basic plots. So the first plot shows you the world, and you see these earthquakes are somewhere here in the Europe. And let me make a local picture. You see now I define here a local. And I generate a figure of this. And these are my earthquakes with magnitude and depth. Color is depth. So if you are wondering, so this local means that I want this local map. H means that I want high quality, and the method, the cartopy that this is a Python library that you installed, and it's used for making plots, maps. Of course, as I said, these are very simple. I mean, these are just to check what you are working with, for if you want to, make a nice picture for a paper. There are different ways how to generate this. Okay, and now that I have my catalog, I can save it on the hard drive. I just call my catalog and .write. I gave it a name. Oh, shit. This is the name that I want to use, in a format. So normally today's standards, more or less, when you work with earthquakes, you should use this Quake ML format. So there is a link up here. No, somewhere in this text I put the link to what Quake ML is, because if you save the earthquake in a Quake ML format, then all this information that I was showing you before this will stay intact. So you will have a catalog that is a list of events, and each event will have all this information inside. But if you save it as some other text file, normally you will only have information on location, magnitude, and time. and sometimes this is not enough. So okay, now I saved this file on my disk. It's located in the same folder where my Jupyter notebook is, because I didn't specify anything here before, the path to the file. And this is it. Okay, so we now have our catalog of earthquakes on the hard drive and stored also in the memory. And now we can go further. So now let's look at the, different parts of this catalog that I was talking to you about before. So let's say we want to look just first earthquake in our catalog. So my catalog is, if you remember from before, is 995 earthquakes long. So it has all this information, but I just want to, let's say, look at the information of the first one. So what I can do is I define here my event. So this is the first event. Because I take the catalog, I take the list of events, and I take the first one. So in Python, 0 is always the first element in the list. And then I print the information on this. So now this is different. You see, we have only information on this event. And on quick look, we have timing, origin time of the earthquake, latitude, longitude, local magnitude. And then we have some identifiers that come from the catalog provider. So it says, yes, this is an earthquake. It has some certain entities. It has some description. It has some origins, and it has some magnitudes. But with this text, we can't really do much. So if we now we have this event, okay? The event here is this. And now we can look at the origins of this event. So we take the first in the origins list. And you see now we have only information on the timing, longitude, latitude, depth, and so on. Here the quality tells us, okay, this was detected on 13 stations with some standard error of 0.2. And you see here in the origins, we have this time. And if we write like this, event.origins.time, we get our UTC date time object. Like we defined one here for the catalog, start day of the catalog. This is the UTC time object. And the same here, when we look at earthquake itself, the origin time of the earthquake is given as a UTC date time object. We can look at only the depth. It's 15,800 meters. We can look at the different magnitudes. And because there is only, in this list of magnitudes, there is only one magnitude, we can take this Mach value, and you see it's 1. So we can, inside of our catalog, we can get all this information about one earthquake. Now, we save this catalog on the hard drive. You could also read it directly from the hard drive. And as I said before, if it's in a QuakeML format, then you can access all these things that I write here. But if it's in some other format, maybe you will not have information on, okay, these are some very simple informations. You will have all of them, but you will not have information on peaks, because in a simple text file, this is very hard to save. Okay, so the next thing is the station inventory. So this is to get, to download the station info, the metadata of the stations. We use this station inventory. So you can get information on majority of the networks on either Orpheus, this is European site, or FDSM, this is American website with the information on the seismic network. So let's check this FDSN. Okay, it's slow. maybe the other one will work better. Okay, so this is Orpheus, the European one. And if you click on that link that I post there, this is the information, the website you get to. So you can check permanent networks, you can check only temporal networks. Let's go to permanent one. You see there is 12 pages of this. You can see where this data is coming from. Let's say you're interested in Albanian seismic network. The information actually comes from Italy, not Albania. Here you can cite this. You get information how to cite, and you can also search. I don't know. Let's say we want to check if there is some African network. We have
Ghana.
Mm-hmm.
Ghana.
Ghana. Okay.
I don't know if you have.
Ghana. So here, on the Orpheus node, but most likely if we go to FDSM, the data should be there. Just a second. Let's see. Services. I need to get to the correct. Oh. Just a second. FDSM. Okay. This is the same website. Network codes, yes, this. So let's, this is the FDSN, the American one. And here, let's see, Ghana. Search. Okay. So you have, there is this Ghana Digital Seismic Network. It's run by Ghana Geological Survey. And here you have a network code, GH. So now if you click here, let's see. Okay, you can see that the data is available for these stations. And these are the seismic, here is a map of seismic stations. So the inside of this seismic network, 1, 2, 3, 4, 5, 6 stations are running. You can see here the name of the station, the latitude and the longitude, and the data provider. So you see, you have it in Ghana. I don't know if this is actually, but the problem here now is I don't know if this is actually open. So can you download this data or not? You can, later you can try to get the data from these stations and you will see if you have some problems. Maybe this network is not open because here on this website, you will have information on all registered networks, but not necessarily open. So they can be closed for everyone.
Okay.
Yes.
So you can have access to it.
Yes, if the network is closed, then you cannot have the access. But sometimes what you can do, you can still download data networks that are restricted. But you need to get a password from the, let's say, Ghanaian Institute.
Okay.
Yes, but this is, you know, this is different for each closed network. So I cannot really tell you how exactly this is done.
Thank you.
Okay. So now here with the inventory, it's the same as with the events. So you have an inventory file. Within this file, you have networks because inventory can consist of different networks. So we take the first network and inside we will have the code of the network. So in this case of the Ghana, this is GH, and some short description. Maybe, I don't know, it will say this is Ghana Digital Seismic Network. And inside of this network, you will have stations, and each station will have information, the code. So this is the name of the station, location of the station, when did the station start, when it stopped, or if maybe if it's still running, this end date will be empty. And then inside of the channels, so each station has multiple channels, as you maybe know. So let's say a classic seismic station, broadband seismic station will have at least 3 channels. One is vertical, it records the ground motion on the vertical component, and 2 are horizontal in the north direction and east direction. So these are these channels. And for each of these channels, you will have information like the code. So let's say for vertical channel, you will have BHZ or HHZ. You have the location, which will be the same as for the station. You have azimuth. If you are working with horizontal components, you need to have the azimuth, because let's say if you want to do some study, sometimes you need to rotate the information. You will have the sampling rate of the station, and what is very important is this response. So you will have information for each channel on this response. I will show you about this response later. Okay, so now let's see. I want to download, because I'm from Slovenia, I want to download data from Slovenia. Let's see. There is a seismic network of Republic of Slovenia. This is the description. Blah blah blah. It says too much, and I can see. Okay, the network name is SL, and here is the map. ICTP is here, and this is my home country, and this is the seismic network we have. So okay, let's download the stations from this network. Here I define the network name and the client where I want to download this. So let's run it. And similar to before, I call client.getStations, but this time I put here the name of the network. Stations, here I put star because I want all the stations that are available, and level, here I put response because I will also want to have the response from the station. Why they offer this? Because the response is a very large file, and sometimes it takes very long to download, especially for large networks. So let's run this, and it will take some time.
Please. Where the client is client.getStation, we want like this. That's where the stations we want to collect our data from, right? So
yes, here we got the information on this iris. Oh, sorry, on the FDSN, and here I define client as iris. Iris is actually a data provider from the FDSN. I could write here Orpheus, so this would be the European one, because let's say if you would want to get data from Ghana, you would have to write here Iris.
Okay.
Because Iris is a consortium of all this. FDSN is under the Iris, and this is where you get the data. For most of the world, you would use Iris. If you are interested in local networks in Europe, you use Orpheus. Here, the data is now downloaded, and I print the object, the SLNet that I...
In network, get station network equal net. What does net?
Yes. We defined net here. Net is just a string, and this string is the name of the network. So this FDSN code, SL, for Slovenian network, this is SL. And I defined this here. And then here you need to specify what you're looking for, and I do it like here. This I could also do just like this.
Yeah. Okay. You stored it in.
I stored it in this variable. Okay, so now the data of this network is downloaded. You see there is 25 stations. Each of these stations have multiple channels. You see altogether there is 1026 channels. Why so many? Because these stations have different sensors on them. And also this information is for the past and current stations. So let's say if station called voice, this one here, it stopped working at some point, they changed it, they put inside new device, but the station, the location stayed the same. So inside what in this inventory, it's saved. Inside of the inventory, we have data for the change stations and the currently running. Because let's say if you want to download some old data, you need to work with different information, the response that I will show you later, than of the current station, even though the location is completely the same. Okay, so there is a lot in this, and we can save this like the catalog. We just use the .write command, give it a name, and use the station XML. Before, for the events, we used QuakeML, which is a similar thing as the station XML, just for, you know, one is for catalog, one is for station information. And again, inside of this big station XML file, we will have all this information here. If we would save this at some other text format, we would lose information on the channels. Because this is really, really huge data that needs to be stored in a correct way. Okay, so let me save this. Okay, it takes some time because it's a big file. Now I can make, similar to the events before, I can make a very simple plot of this network. So it should look the same. I mean, not the same, the locations should be the same as on this one. Yes, here you see Trieste is here, this is Slovenia, and these are all the stations that we downloaded. We can look at the code of the network saved on our hard drive. We can read the description. It says Seismic Network of Republic of Slovenia. Okay. We can look, let's say, if we do it like this, we get information on all the stations that we saved. But let's just look at the first one. So the first station is called Boys. So this is the code, and it has these available channels and has a latitude and longitude and elevation information here. Access, you can see it's open, so this means that we can download the data from this station. So let's see the code of this station, Boys, as I said. The latitude is here. Channel 14, so let's say this is available channels, and you see there's a lot of them. And if we look at the 14th one, it gives you the information. This is horizontal east. This exactly 14th channel started to work in 2015, and it's still currently running. Azimuth is 90 degrees from north because it's east one, and it has a sampling rate of 200 Hertz, and it uses this sensor. So, okay, HHC, sampling rate of this channel 200, and now the important thing, the response. You can see, okay, the channel 14, so this HHE channel, information on the responses that is here. You see, we will talk more about what response is later, but just first information. Sensitivity of the device is defined here. There are 3 stages that are used to compute the shaking that is detected by the seismic station and put it to meters per second. And let me make, you can also make a simple plot of this response, and you get a file like this. So does any one of you know what this instrumental response is? Did you talk about this with Fabio maybe, or? Okay, so basically, just by looking at this picture, right? As I said, later we will go a bit more in detail with this response because you need to understand it to work with the data. But basically from this picture, let me make it a bit bigger. in the plot, I have to specify here minimum frequency, so 0.001 hertz. So this is this left side is at 0.001 hertz. And these lines, what they represent, let's just look at the amplitude spectrum. We see that these low frequencies, we have this line, while here at higher frequencies, so from 10 to the power of -2, the response up to somewhere here is completely flat. So this means that our seismic station can record data very well in this part, so between 0.01 hertz up to 100 hertz, slightly less. So what we record on the raw data, so without this removal of the instrumental response, it's okay in this frequency range. But if we look at the lower frequency signal, let's say you're interested in tomography of noise generated by noise, you will do this with Daniel later. You need to remove the response because the waves that you see that are recorded by this station are not recorded correctly. So you need to slightly amplify them, otherwise the recording that you get is wrong and your results will be wrong. But as I said, we will talk about this later. Then the other side here, you see that this drops to 0 very fast. Why is this? This is because our seismic station is recording at, where is this, at 200 hertz. So this means that it can only record, because of the Nyquist frequency, it can record only up to 100 hertz. So everything above 100 hertz is wrong. It's not. It does not hold any information for us. So when we are working with the data, let's say we have data of the station with 200 hertz sampling rate, we can remove all the information above 100 hertz away. And you will see this is done with filtering that we will look at later. This will make the data set smaller. So if you store it on your hard drive, it will take less information. And also our earthquakes are only, up to, let's say, 40, 50 hertz, not more. But the lower cutoff is more interesting, that you will see later. Okay, so the last main part of OpSpy are the seismograms, so the recorded data sets from the seismic station. Again, before we had the catalog, we had the inventory, and for the waveforms themselves, we have object called stream. So stream is it's basically a list of traces, and you will see the trace is all the information that comes from the recorded station. So let's say if we have a stream of one station, let's say we select only one station here in our Slovenian data set. Let's say we want to look at this Boise station. If we download the data only of the Boise station, our stream will be a list of traces all from the same station. So we will have, let's say we look at the broadband channels, we will have stream that is long 3 traces. So the trace of vertical and 2 traces of horizontal. And all this information is stored inside of a trace. So let's say if we look at the first trace, we will have the raw recording. This is a NumPy array, so just a list of numbers of the recordings. And then we have objects called stats. And inside of this stat, we have all the information like the network name, the station name, so we know where this was recorded, channel, which channel we are looking at, a sampling rate, in this case, 200.
Please, the traces, the signal is discretized. That's why they are storing it in an array.
Yes. So you will I will show you the traces later. But so basically, you have for at 200 samples per second recording, you will have 200 measurements. So the sampling rate is 200, and the delta t is time between each of these samples. So this is not, it's not a continuous recording. You cannot do this with this any kind of instrument. So this is just a recording at very, very, very high frequency. Let's say in this case 200 samples per second. Today the fancy seismometers that they use, let's say for glacier monitoring, have frequencies even up to 500 or sometimes more samples per second. So this is really, I mean, you can say it's a continuous signal, but it's not. So it is discretized. And okay, then, yes, as I said, you have the sampling rate and delta. This delta is automatically calculated out of our recorded signal. We have number of points. So let's say if we record 1 day of data, we should have number of seconds per day times sampling rate. So a lot. And then there are some methods that we can apply to our trace. So let's say taper. This will force our signal to 0 at the beginning, at the end. We can filter our data. We can resample our data, integrate, remove response, and so on. You will see some of these methods in work later, how they work and what they mean. Okay, so now let's look at these waveforms that we can download. So because this is, waveforms normally of classic seismic station 1 day recording, and 3 channels are around 15 megabytes in size. So I will only download data of 1, 2, 3, 4, 5, 6 stations. So it does not take too long, but for what we will do, this is more than enough. So inside of this variable, the list, I define the names of the stations that I know of inside of my inventory. Where is this? So let's run this. And then because this network is located in Europe, I need to use this Orpheus. Otherwise, I could use Iris. Let me write this here. So I will use the Orpheus, and I will download just 5 minutes of the data. So you see here, before I had here for the catalog, I wanted 2 years. So I went from 2018 January 1st to 2020 January 1st, but now I just want to look at the data of 31st January 2019 between this time and this time. So you see this is 5 minutes of data. So let me download this. Okay, so the way how this is downloaded, now it's downloading. You see it's downloading the first station, and this will write down when the rest of the stations are downloaded. So the simplest way to download multiple stations like this is this kind of for loop. Basically, it loops through our list of stations, and each time it calls this client that we set here and the get waveforms method on this client. So inside I defined the network, which is the same as before. So SL for the location. This is some, I don't know, I never saw this in action, but more or less you always put star here because you want all available locations of this station. The station name, which comes from this list. Channel, here I put HH star because I want only HH channels, so the broadband high sensitivity channels. These are 3 channels, like I said before, vertical and 2 horizontal. And then the start time and the end time of interest. So now, and then for each of
the station name.
Yes.
You wrote STA. So you have to write this specific station name, or if you want to download all the data.
So in my case, we put this, you see, we have stations here. And with this for loop, we loop. We first take this station name and this station name, and then this station name, and so on. But you could loop over the inventory that we downloaded before. The problem is that it holds, I don't know, 25 stations, and on my computer, on my internet, this would take too long time.
Where is the variable STA?
It's this for loop. For for
okay.
STA in stations. Stations is this one up here.
Okay.
Yes, and then it goes. First it takes this one, say, then it takes GBus, then it takes JAVs, and so on.
Okay.
And now, you see, now it says here I put this print selected stat. So this is this stream object that we created before, and it finished now. You see, it's downloaded this data. So this is 18 traces. So basically, how many? What did I say? 6 stations, and each of these stations have different 3 different channels. And here you have basic information of time when this data is, so 5 minutes, 200 hertz, and this is the number of samples that was downloaded. So let me just run this for later use because I want to save. The same as before, with all the catalog and inventory. Also here we have this write command. So I will I downloaded this data and I will save it now in one of my folders, so I can use this later. Okay, and now let me plot this 5 minutes of data. So I call the function that I defined. Inside I put the name of the stream, and these are some other informations. Now I should get a nice plot of 5 minutes of the data that you can see here. And already here you see this is an actual earthquake that was recorded by these 6 stations. Okay, I can make a print. We already said, we already did this before. So now I can select only one trace out of this stream. So let's say I want this, say, HHE. I know it's on the first item in the list. So I select it till 0 here and print. So now you see inside of the trace, I have only this channel. So say station with HHE. And I can now look at directly the data that I was showing before. So this is now an array of actual recordings. You see it has many, how much, 60,000 samples inside. And these are the actual values in the integer units. So this is what you see here. Yes, the first one. I can look at the stats information about this trace. So you see it was recorded on this station between this and this time. The delta is 0.005 second. And these are the things that we're interested in. Let's say if you want to extract the number of points, you do this stats.number of points, press enter, and you see you get this value. Because you can always store this for later use. Let's say, now I can anytime store this, get this information, right? And now I was saying before about these methods that you can call on the trace itself. So let's say we look at the resample method. So we select our stream of data, so all this information here, and we resample it to 0.5. what does this mean? So this means that, let's say, original data should be, if I write here 200, nothing will happen because the sampling rate of this station is 200 hertz. If I write here 100, it will downsample the data to 100 hertz. But to see some really big effect on so many traces at once, I have to put very low. So now this will be 0.5 samples per second. So basically 1 sample every 2 seconds. So let's run this. Okay, and now let me plot this new trace. You see, now you don't see anything on this because we lost so much information with such a low sampling rate that earthquake, a small earthquake, is not seen here. What we do see here are just low, long period waves. So these ups and downs, these are very long period waves. And maybe here you can see this kind of sinusoid. So this is it from the first introductory part. So if you have any question about this before we continue, yes.
No, the waveform, where we selected only one waveform.
Here.
Why did we select only one?
Just to show you, you can select anyone if you want to. Let's say select the last one. Voice.
So like that place, I don't really get it. Like, how will I know that I want to work? Maybe I want to work on this station and the waveforms are like, what is the criteria for me to base on to choose that? Oh, okay, let me work on this one.
No, this is, look, let's say another way is to, let's say, okay, let's do it like this, boys. So I downloaded 6 stations, okay? So inside of my stream, which is called selected star, is information on 6 stations. So now let's say if I want to get information, I only want to work with say data, so single station, then I can do a selection here. Let's say like this dot select. So now I can, inside of this boys, sorry, say, let me write it like this. Inside of this object will be now our selected star, but only the station that we selected here. Now let's say, okay, you see, now we have just this free information. But still, this is now a stream of data which holds 3 traces. And now if we want to look only at first trace here, let's say for some data analysis, I can do it also like this. So I have only this one.
Okay.
This is, here I'm just showing you things you can do. This is just, let's say, if you want to do some data analysis, you see how this is simply done. It's not it's easy to access different parts of the data. Of course, if you look at it just now, I mean, it's not doesn't tell you much, but in the next slides, I mean, next Jupyter notebook, you will see why we need to know how to split the data and so on.
Oh, okay, thank you.
Okay, so any other question? Okay, then in this case, we can maybe, let me see how much time we have, 20 more minutes. Okay, so maybe let's just look at this instrumental response now, so you will understand what it does. And then tomorrow we continue. So let me start this Jupyter notebook. Okay, so as you remember, before I saved the station information file in this with this name in my folder, so you can see it here. So now I want to read it back in memory. Take some time because it's a big file. Okay, now I can print it here. You see, I have the same station information file as I had before. Okay, so now, as I showed you before, we can make a simple plot of this response. Let's say we want to see the response of one particular station. I access this in this very complicated way. I select the minimum frequency I want to plot, and the output should be in velocity because this is the simplest to explain the response. So as you can read here more information, and here is a link to the Wikipedia page with a very long explanation of these Bode plots. So this is called the Bode plots and basically shows you amplitude and the phase response of our station and so on. I also mentioned the Nyquist frequency before. So it's half of the sampling rate. And it's where we can really record up to where we can record our data, not above. Okay, I already also mentioned this before, the stages and so on. So now let's see what happens when we make a response removal. So let's say we will download some, we define Iris as a client, we define a start time. So there is a recording, I think this is from the Sumatra earthquake in 2004, so magnitude 9. We only want the duration that we will download the data for is, this is 5 days. And this is how we download. So we will take a network called G. Let's see which network exactly this is. Oh, it's, sorry. So this is a geoscope network. This is a network located everywhere around the world. And we will take only one particular station called Cannes. Let's see if it's easy to find. Canberra, Australia. So this one is here in Australia. So earthquake happened here in Sumatra, and the recording will be here from Australia. So we take the LH channels. So what is this? The LH are very, very long period sensors. They are only available in some selected stations and record at very long periods. So let's download this. Let's keep this part. This does not, sorry. And then I want to also download the station metadata. So I create also the inventory file with the same information. So I want network G, station name CAN, only the LH channels, and level response. So I get the response data. Okay, so let's download this. Should take some time, but not too much. I hope my internet did not decide to not download this. Aha, okay, it's done. And now I can make a, let's say, let me first make a plot of all the data. So now this is the free channels. And because we started to download on the day of the earthquake, it's here, and this is the 5 days after. We can maybe make a better plot by specifying this. Let's make it like this. Yeah, okay, now I will make a plot zoom on this. So this is now the Sumatra earthquake, but just as you see, 1 hour recording. So you see how long the waves were traveling over the seismic station. Yes, it's 1 hour. So what I did here, so I took my original stream that I downloaded, I sliced it. You can see in the manual of OpSpy more about this. So what it means, I cut just a small part of the data, and then I call a taper on it. So it will put everything at the beginning and everything at the end. The last 5% of the data will put to 0. Then we filter our data with the bandpass filter. You will see more on filtering later, with the minimum frequency here and the maximum frequency here, and then we make a plot. So now you see this is now a recording of the earthquake on very long period waves recording. So now I can remove the response. So I take my original stream and call this remove response function. So this is it. So now what will happen is that I take the raw recording, which does not have a physical meaning. It's just some values, as you can see here, some very strange, very high and very low values. This is called counts, because it just comes from changes in electrical in volts, and then you need to change this to meters per second. So I remove the response in this way, and I set it to velocity, so meters per second, and I can make a plot now. So now you cannot, you should see some differences between these two, the original one and the one with removed response. The big
I cannot hear.
Just a second. Just a second.
Okay.
Can you hear me?
Yes, we can hear you now.
Okay, I don't know what happened. Okay.
I think it's the network.
Yes, this first of all.
We couldn't hear you.
My problem. But now you hear me, right?
Speak again and let's see.
Yes,
hello,
yes.
hello. Okay.
Now we can hear you.
So now, as I said before, this is here in the original recording, you have some very strange values, as you can see here, right? From 500,000 to minus 500,000. So these are counts, doesn't say anything. But now that we remove the response, we get these physical units. So 0.0003 meters per second and down to minus 0.0003 meters per second. So this is the velocity recorded during this earthquake on this seismic station. And you can also see that, let's say in this example here, these long period waves here, no, on which station? Yes, I think on this one, the coda of the recorded signal is not, yes, you see here this is not so big compared to this. but if you go to here, this is slightly bigger. This is because these are some very low frequency waves that were, after removal of the instrumental response, amplified. So now they are correctly displayed and correctly calculated. So what we can say about this, so if we look at the amplitude spectrum at some very, very low frequencies, we can check how the normal modes, you know about normal modes from Fabio, I think. We can look at the normal modes of this signal. And you will see in this way, you will see what actually happens during the removal of the response. So let me call this code that I prepared for plotting the normal modes. So this is a raw recording. You can see that here at very low frequencies, you have, the peaks are like this. So these are the 5 peaks of the normal modes. And then if I plot the same, but with the removed response, now you can see that amplitudes are much larger. Before it was 0.2 to the power of 10 to 7. Yes, okay, now this is correctly, these are now in correct values. So basically, as I said, we can, by removal of instrumental response, we get correct information on very low period, long period waves. But in general, we do nothing to the part of the response which is flat. So in this part, we do not do anything, but we correct this amplitude and phase in this part. So now this high frequency and low frequency things are comparable. So this is the same thing showed in few steps. Let me run it. So we only take the vertical component now and we change it to displacement. We don't want the velocity anymore. And we see that in the first step, yes, in the first step of the removal of the instrument, this is a raw recording. So we do not do anything with the data, and this is how the data looks like, okay? Then we make the first step in the removal of the instrument response. So we only correct the data beneath this red line. So we get this recording, and then in the third step, we only correct this data here at very low frequencies. And as you can see, now we can see these very long period waves, which were before not visible on our recording. So, okay, this is it for today. If you have any questions, please ask, and we continue tomorrow.
Please, I have a question. It's not about the current lesson. How the exam will be?
Yes, I don't know yet exactly how this will go, but last year, so each of us that lectured, so this week I have lectures, next week someone else have lectures. Each of us prepared, I think, 5 questions, and we sent them to you and you answered them. From my side, I think this year I will give like 3 questions and 2 small exercises. And then you can work on this, and you know, you can work together, because I don't, I mean, here this is not very new information, it's just how to get it and how to calculate stuff. So you can work together and make life simpler for everyone, and you will have few days to finish the exam. It's not 45 minutes, but because I know you have to work with some codes, it takes time to do this. So I think that, I don't know exactly when the lectures finish. I think you have 4 weeks, right? So if you have 4 weeks, this is 1 month, I think. So you should finish by mid-May, and then I don't know, exam. We will send you the questions, and you will have 2 weeks or something like this for to answer.
Okay, okay,
Mhm.
okay. Thank you.
Yeah, no problem. So, anything else? Any other questions?
Yeah. So when we open the Jupyter, like the document, I don't know whether the codes you are using, your codes.
Yes, I will send this code to everyone today. The Jupyter notebook that we used. The first one I will send to you. The second one I will send to you tomorrow, and so on. So expect an email from me later today with this introduction that we had before.
Okay. Thank you.
Okay. So if no one has anything more, we meet again tomorrow at the same time, same place. So take care.
Okay, ciao.
Bye.
Wow.
Bye.
Thank you. Bye.